all, Dr. Jekyll and Mr. Hyde. So here you can see two pictures of them. But before starting, I want to thank also Mr. June Lim, that is actually my mentor. So how I place the picture is just randomly chosen. So even if I didn't finish yet my PhD, so that's not personal, June. So just to tell you. But first thing, why are we speaking about oxygen and why LBE? So as Gert said, so here at SEK we are working on the MIRA project, and I will be short on this. So lead bismuth has been chosen as a primary coolant and spallation target for this project. So first of all, why Mr. Hyde and Dr. Jekyll? Well, probably you read this novel of the early 19th century, and Mr. Hyde is actually defined as a strange and ugly guy. And if you look at LBE, and if you do not control the oxygen in LBE, and you have too much oxygen in the system, what you can get is a formation of slag, like you can see in the bottom pictures, and this can bring to what we observed in 1968 in a big accident in the first submarine that was cooled with lead and bismuth. But Mr. Hyde is also a deformed guy and violent guy. What do I mean with that? Well, if we, on the other end, have a too low oxygen concentration, we can enhance a process like corrosion of the steel in contact with the LBE, and this can bring also to erosion. But on the other end, we have also the Dr. Jekyll, that is an handsome guy. So LBE in controlled oxygen atmosphere looks shiny. So this is the handsome part of the LBE. And is also friendly. So if we control oxygen, we can minimize the corrosion rate and the dissolution rate of the steel. So here shown on the left-hand side, in contact with LBE. So we have in between what is called spinel, is some protective oxide layer. So has come from the movie. So we have Dr. Jekyll and Mr. Hyde is a controversial story. Oxygen, depending on the content of oxygen in LBE, will behave as the Dr. Jekyll or the Mr. Hyde. So what do we want to do? We want to tame oxygen. So how do we do that? Well, luckily we have thermodynamics that will tell us that. So if we know the temperature range in which we want to operate, so here at the bottom of your graph, I said what we want to avoid is to have too high oxygen concentration to avoid lead oxide formation. So in fact, is the red line on the top of the graph. So above this line, we will form lead oxide, and this is not a condition we can accept or we do not want in the operation with LBE. On the other hand, if you have a too low oxygen concentration, we have dissolution of the protective oxide layer, and actually we can enhance the corrosion of the steel in contact with LBE, and this is represented by this black line. So you understand that the boundary and the range in which we want to control oxygen is actually defined by this window, and is defined by the temperature of operation, of course. So once we define the boundaries, how do we do that in reality? Well, in reality, we need to measure this oxygen concentration in LBE. Reason why we have oxygen monitor system that are actually oxygen sensors and that are immersed in our LBE. So the signal enters a controller, normally a PID controller, and this acts directly on some kind of adding or removal of oxygen. So how do we do that? Well, there are different methods. So the first method is the gas phase. In the gas phase, we can have a gas injection, a direct gas injection, and we can either add oxygen or extract oxygen from LBE. We have a solid phase method in which we use the lead oxide mass exchanger. In this case, we can only add oxygen by controlling the dissolution rate of the lead oxide. But so there is space for another method, and in fact is the one that we will speak the most about it. So what I want to stress here is that this method is well known in the world. but for the first time ever has been applied at the LBE for an LBE technology. So and this system is what I like to call EPO, that is electrochemical pumping of oxygen. So the characteristic of such a system is actually a flexible system because it can add oxygen and extract oxygen from LBE. How does it work? Well, the principle is explained in this picture. So first of all, we have a material, special material, that confine our LBE from a compartment in which we have air and a reference electrode. So the property of the material in between is what we call solid electrolyte. So the property of the solid electrolyte is that can conduct oxygen ion. So this material can conduct oxygen from one side to the other. And how does this work? Well, actually, so the green dots are actually oxygen. So on the right-hand side is oxygen atom dissolved in LBE. On the left-hand side is oxygen molecules. And so if you apply a certain difference of potential, we can drive this flow of oxygen ion from one side to the other. And how do we calculate that? And what is the amount of oxygen we transfer? Is actually related to the ohmic law. So it's just dividing the applied potential by the resistance of the cell. We can have an idea of what is the current and how much oxygen are we transferring. So this is all nice when we see it on this picture. The theory is nice, but the first thing is, does this work really? Well, luckily we have a lab in which we could test some different things. So the first study is the feasibility study. We did it in stagnant LBE. And what did we do? So we wanted to control oxygen. And so to do that, we need an oxygen sensor that is actually measuring the oxygen concentration. How does it do that? By measuring a difference of potential. Then we have a controller, the PID controller. And the PID controller is actually acting on the oxygen pump. So the oxygen pump and the oxygen sensor looks alikely because they are actually made in the same way, but they work differently. So for the oxygen pump, we apply a difference of potential, and then we measure the current. And the current is going to be proportional to the flow of oxygen we will have. So in this test, we use a steel specimen. But what are the results? Could we control or not? Well, the response is yes, and you can see it from this graph. So the blue line is actually the electric potential measured by the sensor. And unfortunately, I'm not sure you can see the dotted red line under it. That's the target value. So in fact, we could control accurately the oxygen concentration. And in this specific case, we actually add oxygen. So we wanted to increase oxygen in the system. And on the bottom of this graph, I show you the current that we measured. And the plateau reached depends on the oxygen concentration level. So from this test, we thought, this is amazing. We can control oxygen, we can add oxygen. But I said before that the characteristic of the EPO is that we can also extract oxygen. Is this really the case? So we had some doubts from the first test. So reason why, we actually did an efficiency study in the Checkmate facility. So the Checkmate facility is actually really similar to what you saw before for the feasibility study, but we decided also to study the characteristic and the response of our pump adding a stirrer. So what are the tests we perform in this setup? Well, the first test, we decided to change the applied potential, so the driving force on the pump, on the electrochemical oxygen pump, to see what would be the response as function of the condition and the oxygen concentration in LBE. In the second test, we actually decide to check what were the response of the pump when we use the stirrer, so in different flow dynamic condition. So from the first test, we actually extract oxygen. So I want to remind you that we wanted to see what was the effect for the extraction. So by changing the driving force, we can see that there is a response, a different response of our oxygen pump. So the efficiency is increased, because here I'm plotting the current, the total current we can transfer. So the efficiency is increasing. But if you remember for one of the first slides, when we look at the mirror operating range, so we are operating at low oxygen concentration. And here it looks that the applied potential doesn't play a role. And in fact, there is a mass transfer limit in LBE. So if there is a mass transfer limit in LBE, there are two ways to improve this. So either we change the fluidodynamic, either we increase the surface area. So if we change the fluidodynamic, this is the results we observe. And in fact, this is confirming that at low oxygen concentration, there is a limit of mass transfer. So increasing the rotation speed of the stirrer, we can improve the efficiency of our pump. So by looking at the first two studies we performed, we had a good idea of how an oxygen pumps work. But this happened in a small pot. A small pot, that means half liter of LBE. So it's pretty small. But our goal is to move to something that has 700,000 liters. So there is a pretty big factor of difference. So we thought we need to test this in a bigger loop. And we moved to a nice loop that we have in the TCH hole. That is actually the Mexico facility. So how does Mexico look like? So in a 2D graph, so there are mainly three regions, and they are based on the temperature at which we are operating. So the blue region is actually the coldest part of the loop, in which we have the filter and the pump. Then we have an intermediate region where we have a test section, one oxygen sensor that will come back in the analysis of the results we have from the operation. And then the other part where we have the oxygen pumping system installed. And on the right-hand side, this picture is actually showing you how does it look like in reality. And this oxygen sensor placed on the other part is the oxygen sensor we use to as a target. So this is telling us which is the target and how we control the oxygen concentration. But let's look at the result. So initially, so first of all, we have to focus on the red line and the blue line. Those are the oxygen concentration measured by the two sensors, so that I mentioned just in the previous slide. So the red line is actually the oxygen concentration in the other part of Mexico. The blue line is the one in the colder part. So we started from an oxygen concentration of around 10 to the minus 6 weight%. And what we wanted to do was to reach this dotted line that is actually our target value. So we start operating, applying a certain potential to our pump. So in the bottom part of our graph, we see the current profile. And here we had a certain current. And the efficiency of our pump, so the total current that we could have from the pump, was proportional to the changement we have with the concentration. So decreasing concentration, we see that the current is decreasing. But this was expected because we have a mass transfer limit in LBE. When we reach an oxygen concentration of 10 to the minus 6 weight%, we see that the current is almost zero. So at this point, what do we want to do? So we want to go further, but those conditions, and it is important for me to say that, in those conditions, the oxygen concentration is actually higher than the saturated condition in the coldest part of the loop. So it means we are forming lead oxide. But I said before, we don't want Mr. Right. So what did we decide to do? So we need to test the controllability of such a system. So we decided, and we needed to do something. So at this point, we thought we will change the applied potential on our pump and see what was going to happen. So we knew what is going to happen. So in fact, you can see from the graph, we have a peak in the current, and the oxygen sensor at the other part is actually going rapidly to the target value. Well, the other sensor, not yet. So first of all, how this is happening? Why? What changed? Well, when we move from 2.2 volt to 3 volt, we are actually passing from the equilibrium line, that is the decomposition of our material. when I speak about the composition of the material, I'm speaking about the zirconium oxide that is in our material. When we decompose it, it means we are actually decomposing the zirconium oxide. So we make free some zirconium that gets into our LBE. And when it gets in contact with our LBE, it oxidizes with the oxygen that is around in our system. And this is able to reduce the oxygen concentration in the loop. So why the blue line, so the sensor at the coldest part, is not going down as is happening in the other part? The reason of that is because in the previous part of the test, we formed lead oxide. So, and the lead oxide is a source. Means we are still giving oxygen to the system. The pump is extracting oxygen, but we need some time to extract this lead oxide that gets again dissolved in LBE. So when we reach the target, you can see that our pump is going to a value of 0, so it reached its own equilibrium. Afterwards, we decided to change the target, so to increase the oxygen concentration, and as expected, we had no issue at all, so to control at a new target and adding oxygen. And afterwards, we went back to the same target value that we set in the beginning of the test. And we can see that the two sensors are actually at this point behaving in the same way. So it means that actually there are no extra sources of lead oxide. So there is nothing in the loop that is giving oxygen anymore as before. So the main message here is, so this behaves exactly as we expected. From the extraction of oxygen, in the first part, the limiting, the mass limit that we observed in LBE, from the decomposition and the possibility to extract oxygen in this way, and from the adding of oxygen. So this is really a nice result. We were really happy with this. And what is going to be the next step? Well, we started from half liter of LBE, and we thought we want to go to something bigger. So we moved to the Mexico loop, and successfully we could control oxygen. And what is going to be the next step? Yeah, it's going to be the Mira case. So we feel that this technology is ready for the Mira case. And how and why do I show you this? Well, the EPU system for Mira, shown in the picture, is actually a clean system. So compared to the gas phase, we will not have to deal with radioactive wastes. And is a versatile system. We can add oxygen or extract oxygen. It's easy to control. We need to control just the current, electronic current. And is at zero operation cost. So we need just few watts to control our system. So to conclude, hopefully I was not too boring. What I want to say, if we can tame the Mr. Hyde, the only thing that we will remember from our novel will be the Dr. Jekyll. Thanks a lot.